So thank you very much for the beginning here and for the introduction, what you have done. Indeed, actually, before I start, a little puzzle for you. This was instigated by one of the members of the organizing group. I give you a sequence of numbers, and we like sequences. Okay, I start. 2006, 2009, 2012. Arithmetic sequence, I don't know. 2018, 2025. What did I say? Right. These were the 5 symposiums of optimal stopping done by the young school. And we have the hero of the young school here, somebody who was actually in the organizing committee of all 5 dates. In Manchester, in Warwick, later on in, well, he was also in the organizing committee of Philip Ernst, Professor Ernst there, here the one with the blue shirt. He, by the way, did something amazing. He announced 1 meeting, but all those who went there saw it were 3 meetings at the same time. Yeah, and then our last, oh, I forgot to mention the Warwick meeting, but I think Professor Chaka is not here, as I see. And well, for the last one, our stopping time, so far it's a deterministic one, but it won't be the last event, I guess. Thank you very much to the organizing committee having made this possible. Professor Kay, Professor Pesquier again. Philip was not on it, but Professor Lee, I don't know him. Sorry that I don't know the faces yet. This is going to change thereafter. And then, of course, Professor Saunders. Thank you for so much help. Okay, let's go right away. So my name is Thomas Bruss. I was for a long time at Université Libre de Bruxelles. I'm still there, but I was a professor there. Now I'm an invited professor. Unfortunately, that means I'm not paid anymore. I'm just allowed to do research and keep my office, right? So you know what that means. We all have seen that, and the other one is simply the date. If something is not clear, lift your hands. So it's normal that so far there is no hand up. I do something a bit strange. I acknowledge financial support to my university. And the second one is a former student of mine who became my successor. I do that because it is illegal what they do me supporting for that, because it's government money what they have. So please, if you put that in public, take that line off. And the Fields Institute, thanks very much for your. My idea was I should try to really stick to the idea of the how the conference is announced. And so I tried to give something which concerns applications. And from time to time, there are little inlets of deeper things, which does not mean necessarily that I can ask, that I can answer the deeper questions, but you will see. But the main thing is really to show you, with all the things we know already, sometimes we might be in a situation where we say, well, let's live with that, and we will see what we can make out of it. So let the motivating question be, how come that some people seem so successful in recognizing opportunities in making business? Well, it depends on your personal attitude. I mean, a very good way of thinking is they owe it to very good connections there. Secondly, what most people find convincing is saying it is not really true that some people are particularly successful. It's only by statistical selection, you know, that we get attracted to the success. We see those which are successful. So this is a biased selection. Well, the first one is contradiction-free. If you think about it. This is contradiction-free. If you believe somebody has a special wire there, no problem. If we say it must be statistical bias, simply by the selection, that is a very good answer, I think. But if you think deeply, it is not absolutely consistent because there are counterexamples. Now, my personal answer, and I cannot do more than that, is simply say, suppose I was forced that somebody came and say, well, you were teaching optimal stopping and teaching probability for decades and so on. If you were forced to apply it in such a way that people see an outcome, what would you do? My feeling is we have to learn. I'm going to specify later on, nothing to do with deep learning, much simpler. And we must fix an horizon. For me, fix an horizon is essential to get things done, because otherwise I say, well, it was my intention, but I did not. Secondly, we should look for promising objectives. They should be flexible. It should not be too narrow. If you want to be successful, we are working in option pricing. So you should not concentrate by saying, I would like to invent now a formula which allows me that, and I can, no, too narrow. Let's look at promising objectives. And what I want to do is to collect a random basket. And I think this is the little original part which I might have to offer if you ever thought about the problems. And then stick to your method or algorithm to decide on actions. Stick to it. Don't revise your horizon and your decisions too often. Before I get carried away, I better look at my watch. Oh yeah. When is the official end? We started punctually, is that right? So what I see as one of the most flexible and most interesting general objectives is a stop on the last interesting event, because this allows for so many interpretations. Let's look together. So I start formally with the sequence of events E1 to En. Little n so far is known. So we have a probability space and there we have events, but I'm not really interested in specifying what they exactly are. I say, I'm interested in interesting events. You choose the definition. And since the event will not be specified later on, I simply look at the nully random variables, which take values 1 or 0, according to whether it is interesting or not. Examples. Why is the last interesting event often special? Think of the secretary problem. You would like to maximize the probability of getting the very best one. An interesting event is if there is an improvement stepwise of the relative rank. And if you get the last improvement of relative ranks, right, then you are in the maximum. So there's a simple thing. Everybody of you sees immediately for buying and selling strategies. In principle, that's the same. And we are flexible there. Perhaps you are very demanding and say, in a business, I would do not only if it's better, but at least if it's 10,000 Canadian dollars better or so. And you have another preference, and you have another one. We don't define it. Capital investment, if you think about it, when do you, for example, give something to somebody who wants to stand, how do you call it in English again, venture capital, right? You would like to put venture capital somewhere there where you think, if I give that startup that money, I hope nobody else would give quickly an improvement of what they have shown, at least not as far as my horizon goes. I want like something else to show you. And here we get deeper, and you will see the interest of it. What I show you now, you're probably aware of this. I wouldn't say it's anything special, but I'm sure. Do you understand me? Okay, is the following. Compassionate use clinical trials is a word you may have heard before. If people are unfortunately very seriously ill and approved treatments haven't shown any effects, such patients then often come to a doctor and would say, doctor, please do whatever you can do. And the doctor might say, well, I think of a certain treatment, perhaps even with the same medication as those which have been tried before, but perhaps in another dosage, right? And the doctor would say then to the patients, yes, we might try, and I think there might be hope, but I can't tell you anything. In many countries, such things are forbidden. But also many allow as soon as they have a written consent of the patients. Why do I tell about that? Well, suppose to simplify things, a zero is suppose that the result of the treatment are relatively quickly known, say in a week or two, often the negative reactions are quickly to see. Zero is bad. One, yeah, good. And there's hope. Zero is bad and so on. Now look, please, together with me, what happens with the very last interesting event. The very last interesting event, say for here in my sign, so this is simply saying the time where they are coming, right? So here we stop. There are altogether 6 patients in the waiting line. Why is this last one interesting? Well, if you are a conscientious doctor, and if you were a doctor, medical doctor, I'm sure you would be conscientious, you would say here, stop. Because I have collected all the successes which the trial gave me, and I have maximized, if this is really the last one, the number of those which I can send away with good conscience by saying, don't take the treatment because it has in general negative impact. Use the time to try something else. Now you say, but of course the doctor doesn't know that's the last one. But if a prophet or this one told him this is the last one, you agree that that's what you would do as a conscientious doctor. So you see how this objective suddenly switches. It becomes almost, I wouldn't say bidimensional. There are not 2 dimensions, but there are 2 aspects. On the hand, you maximize the number you don't want to treat. That's to say, you do a good decision in that way, but you have collected all the ones. But now you say, yeah, but there are zeros in between. But you're a statistician, you know we can't help. We needed that in order to learn. But if the prophet would tell you, that's the last one, would be there. Please, the only thing what you should do is see and remind that that's an interesting problem. We would like to give very good answers there. Yeah. Suppose now, so I become much more modest. Suppose now we know there will be little n events with probability pk that the case event is interesting, right? What would be the optimal strategy? In 2000 exactly, was the solution given? The solution is the so-called odds theorem of optimal stopping. So here the easy cases, we have independent indicators, and we suppose that the PKs are known, which would not be the case in the last example. But suppose this is. Well, then this algorithm, as I said, proved in 2000, gives the optimal strategy. Look together with me. You define pk divided by 1 minus pk. And that is a probability divided by the complementary probability, so that the English call it the odds. That gives the name to the whole thing. RK, the capital RK, is the tail sum of the odds from the case onwards. And QK is simply the probability that there will be no 1 after k, right? Define now S as the largest k where this 1 becomes greater or equal than 1. Now look with me, you all know what the stopping time is, whether deterministic or random. This is clearly a nice stopping time because this, right, is decreasing in k because I get less positive terms, right? Whereas the other one, these are products of probabilities which are smaller than 1, so that's goes in the other way around. We define it as the largest k with that. And that if R1 greater or equal than 1, look, R1, that is simply the sum of all the odds. R is ratio for, I didn't want to use a little o, so R is ratio for odds. This one certainly dominates the sum of the odds, dominates the sum of probabilities, because Pj divided by 1 minus Pj is always greater than Pj here. That's to say, this is the interesting case. Here we see immediately what happens if even the sum of the probabilities is smaller than 1 in particular, then you should stop immediately. You don't believe that there will actually be results, okay? Now this is the main result, the optimal strategy. Stop at the first AK with that, and the win probability is immediately taken here. With this little s, you plug it in, little s there, and it's simply the product of the two. This result had attracted interest, but I don't know whether it had attracted enough interest that would be justified for me to believe that you know it already. That's why I wanted to give it. It will be central in what follows. It has important probabilities, something which should really be called the 1 over E law, but the 1 over E law is often misused just for the secretary problem. You see, we are in a much more general case here. We have general PKs, right? Interesting enough, that result took even 3 years more to be proved than the original odd theory. So we always have the magic 1 over E as success probability. For us as business makers, we are happy about the following, under the condition that we do select the last one. We have something like 60% chance. So, and under the condition that we select as businessmen, we know what that means. Selecting means I have to buy something, usually, for example, or sell something. If I don't invest, then I still keep my money. And so that's something positive. So this is an important thing. It's overall very powerful. The probability that you get something very good is really large under the condition that you select. If you don't select, you still have your money on accounts, for example, in buying or selling. It has the so-called ace property for us. It's a little bit less important, but computer scientists loved it. Let me show. The ace property means it's an algorithm which gives you at the same time all what you would like to have, namely the stopping time, so the strategy, and the probability, the win probability, as we saw. And you can also prove that it cannot possibly exist another algorithm doing that more quickly. I should shortly say something about it. Oh no, it's wrong. This is people. It comes from the following. I should show you, because after all, this does not happen so often that one has this ace property. We had said we start with the Pn minus 1, and so on. We have done the 1 minus Pn, that we call them in order to form the odds, that in Qn minus 1, say, and so on. And then I form the ratio, because it's of that we tailed the sum, right? And we call them Rn minus 1, and so on. So the computer compute, we take here always plus. As soon as that, in the interesting case, exceeds 1, we stop. But what have we used? We have used all the things here. And in the final answer was a function of this capital R. And no, we have now the S there. RS, QS, just a product. So everything you needed in order to define the S gives you immediately all the things. Yeah. As I said, it's more of interest for compute, but still, it is sometimes nice to know that if you have an algorithm, that you cannot do better. So that's one of the strengths. Let's think together. We will see that. Sometimes we are in more interesting situations. We say, well, actually, I consider the whole thing in continuous time. Let's suppose this is the end of my horizon. Suppose I'm trying to do business by thinking that values go up, as we have seen in last years before Trump, with the clear signs of inflation going up. You would say, well, this might be my guess that prices might develop under the condition that they go. I say it again, under the condition that I'm right with that the trend goes up, that would it be? And what would then be in a certain interval of length delta t? Well, we would, if P is the probability that the trend goes that way, it would be P times F, if I call the graph of this one F, P times F of T minus Ft prime, right? So neighbored distances, so I can do it. What I want to say by this little design, and I think I don't have to go further, you find this trivial, and you're right. In principle, I have only, in this case, a Riemann sum of what I did before. And that Riemann sum, if you choose the delta sufficiently small, will then go to, it's getting an integral form. Instead of saying the first time that I'm going with the estimate, greater or equal than 1, this would be just a time of 1. But okay, just to show the flexibility, you feel something else. If you have now a random number of events, as long as we have independent increments, there's no problem. Think we have a Poisson process, for example. For example, this Ft could now be the inhomogeneous Poisson process, the intensity, which might vary there. You take the same delta t argument, and we are there. But then we get, of course, a random number. We don't have to work with the fixed anymore. We have the Poisson law for the number of things which come. You stop me if I'm not clear. So in continuous time processes, if I have independent increments, I can do a lot. So the only decision you must make is, do I put my stake on, for example, in buying and selling, on increasing or decreasing things? And that these Ft times P times delta T, F of T, say, times delta T times P, would then be the absolute probability of having an interesting event there. So what you see, and I think I should not write any formulas there, you would agree immediately. Continuous time process version for independent increment, things become essentially straightforward. If we have independent increments. Deeper problem. What can we do if the pKs are not known? How then we are with the odds algorithm a little bit of problem, because we have to start at the end. 10 or 5, is that right? That's what I understood. No? Or 10? Okay. No? Okay.
We wrote a 10:05, I think, because we've been generous with the duration of the coffee breaks if we go a little bit
Okay.
longer.
Okay. Well, anyway, if I'm too long, you simply throw things at me. I will understand the message. Okay. What can we do if the pK, respectively the densities or intensities, as I just described, if they're not known? Well, everybody would think that. We are statisticians somewhere. And we would say, okay, for example, if I have seen, I don't know how many IKs there will be, might be even random. But what we know is the following. If we have seen, like in the medical problem there, if we have seen the first result, we can guess on what the intrinsic parameter would be. So the natural idea would be that we estimate, not here we work with the backward thing and looking forward. We see what happens and we estimate the future odds. That's all, not more than that behind, okay? And then as approximate optimal strategy, we stop as soon that becomes smaller than 1. Think with me, we did it that way the first time it went bigger than 1, now we come the other way around. If it's getting smaller than 1, then I have just left a thing that is bigger than 1. So this is the point where we should say, now stop according to our estimation. Of course, not as precise as the other. The probability of winning is then roughly this. How would you model it in a practical thing? I am perhaps very simple-minded. I never, in such cases, if I don't know, I would simply model by linear functions. I would say the probability pk is some probability that I put my stake in the right direction, and the hk, how it would be. For example, if I think there will be inflation, and I think it is still in the right direction, I would choose the hk even increasing. So these hk are deterministic. This is a thing to estimate. So what I say here, I call that simply delta epsilon results. If we are now in the problem of statistical inference, you can say, well, for a given delta, so if I say that the probability of my estimating the p is in the value of delta, I get an epsilon estimate around the probability of winning with it, right? So this one we have. We also have, you are not surprised, we have asymptotic optimality, which is quite useful if the pKs do not become too small, right? That is work I had done with the Lucia, who unfortunately has died 18 months ago, and that's why in his honor I wanted to mention this. It's of practical use. We have small risk of losses. Please do notice we always get of it. What do I mean by a basket? I should give at least that design. I have observed, actually, this means there's an interval I've lived. So now I say today, for example, I'm at Fields. The end of my horizon is the 31st of December this year. So this is the age, right? So how do I collect the objectives? I know not much about things, about art. I don't know much about used Ferraris or Porsche. You do, you love them. I do the following I'm interested in. I'm looking at things I see. Suppose I put an L here for saying this is land. As I said, I think of land. But then suddenly something else. Professor Pesky wants to buy his used Porsche of 1930, which costs a fortune, I tell you. He says, no, these are Porsches or something like that. We did not think of that before. A couple of things we're interested. If we are a larger team, we have many of them. I do it just with arrows. For me, that's little forest parcels without trees on it, and sometimes agriculture. The strategy which I was defining will then be of that form, only that it becomes varied. From this, I look at 2 types. Here, I look at 3 times. These things will develop, and I use them simultaneously. The end of different objectives here, which I have, that is my goal. Oh, yeah. Huh. So do you really believe that we can create values with that? Yes, I do. I do because we have so many interesting independent possibilities in the world. You must collect them, you need a good algorithm. I think it's not a bad algorithm, this old algorithm, the most flexible one. So you may ask, so why don't you stay home to become rich instead of going to conferences and talk about this? Well, who told you that I'm not rich? I wanted to, do I really have the 4 minutes now? Okay. I want to talk about something deep. I underlined the importance for the application of getting some model where I get the independence in it. Often conditional independence suffices. Let's suppose that. Freddy Delban sent me the following result. I couldn't believe it first. A discrete time martingale with respect to filtration with atomless innovations is the infinite sum of martingales with independent increments. Pardon? I said to him, pardon, what do you mean? Any martingale? I give you a martingale with very strong dependent things, and you say this can be written as an infinite sum of martingales with independent increments. Where does the independence then come from? Does that mean that the martingales must be dependent on each other for creating that independence? But what happens then with their increments? I didn't understand something. I must go, unfortunately, quickly over it. Freddy Delban is an excellent mathematician. I always need 3 times to understand him. But I went over the paper, and it is true. He showed step by step. If he starts with a trivial sigma algebra, he was only looking at L2 norms. There exists a martingale sequence in such a case that if this is the original martingale term, I can write it like that. And this one converges in L2. And these martingales have independent increments. I said to him, give me an example. And he said to me, that's why I sent you the thing. He did not know an example. If you have any insight there, what is the logic behind that? How you can create this independence out of such statements? Look, if you have atomless innovations, that means only if you take off the compensator and the martingale, well, then I have a process. You have now independent innovations. We all know what that means. But where does the independence of the martingales themselves come from? Actually, he couldn't give me a convincing example. I have just one, but I'm almost embarrassed to speak about it. It is based on a result Libre and I proved on the last arrival problem. It was introduced via proportional increments. Very quickly, and I promise I stop with that design. Suppose we have interval 0, 1. Somebody, the devil, he doesn't tell us anything. He throws in uniformly capital N points. Right? I'm a sequential observer. I look like that and must stop somewhere. I want to stop at the last point. So it has a little bit to do with our thing before. You and I created a process with proportional increments. Simple idea is, if we have uniform random variables, uniform random variables, we have that the number of points in certain sections should be proportional compared to the rest. And for such a process, when we subtracted the compensator, we had indeed the fact that the remaining thing was a Poisson process. But now everybody of you knows if I have a Poisson process with rate lambda, or whether I have a Poisson process, or I have n Poisson processes, each of them rate lambda over n, that is probabilistically exactly the same. So this is one trivial example which shows that the result of, oh, I must say, yeah. This is clearly it's dependent increments, right? Dependent, because if you have seen much, more likely it becomes that there is much. That's the only trivial example. If you have something stronger, I would be so happy. Thank you. Thank you so much.